All right, this is our last part 3 of the analysis models using Newton's second law. Uh, so broke it up into 3 parts so it wouldn't be too long. Let's look at the next problem, the next example. A person weighs a fish of mass M on a spring scale attached to the ceiling of an elevator as illustrated in the figure. Part A, show that if the elevator accelerates either upward or downward, the spring scale gives a reading that is different from the weight of the fish. Let's read the little captions on the elevator diagrams. When the elevator accelerates upward, the spring scale reads a value greater than the weight of the fish. When the elevator accelerates downward, the spring scale reads a value less than the weight of the fish. So we conceptualize this as follows. The reading on the scale is related to the extension of the spring in the scale, which is related to the force on the end of the spring as in the figure. Imagine the fish is hanging on a string attached to the end of the spring. In this case, the magnitude of the force exerted on the spring is equal to the tension T in the string. Therefore, we are looking for T. The force T pulls down on the spring and pulls up on the fish. Let's categorize this. We can categorize this problem by identifying the fish as a particle in equilibrium if the elevator is not accelerating, or as a particle under a net force if the elevator is accelerating. Let's see, let's analyze this as follows. Inspect the diagrams of the forces acting on the fish and notice that the external forces acting on the fish are the downward gravitational force F sub G equals mg, and the force T, tension, exerted by the string. If the elevator is I lost my place. If the elevator is either at rest or moving at constant velocity, the fish is a particle in equilibrium. So f of y, the sum of f of y equals t minus f of g equals 0. T equals f of g equals mg, that's just the weight. The elevator at rest or moving with constant velocity. Okay? Remember that the scalar mg is the weight of the fish. Now suppose that the elevator is moving with an acceleration a relative to an observer standing outside the elevator in an inertial frame. The fish is now a particle under a net force. Apply Newton's second law to the fish. The sum of the forces in the y direction equals T minus mg equals mass times the acceleration in the y direction. You solve for T, and T equals mass times the acceleration in the y direction plus mg. Mg equals mg says mg equals ay divided by g plus 1. I think that should just be m. No, maybe not. Mg, acceleration in the y direction, divided by g plus 1. Oh, I see. Okay, yes, that's right. Equals fg equals ay divided by g plus 1. So, okay, solve for t. We have chosen upward as the positive y direction. We conclude from our results that the scale reading t is greater than the fish's weight mg if a is upward. So a sub y is positive, and that the reading is less than mg if a is downward. So ay is negative. Okay. Evaluate the scale readings for a 40 Newton fish if the elevator moves with an acceleration ay equals plus or minus 2 meters per second. So we evaluate the scale reading if a is upward. T equals 40 newtons. A sub y is 2 meters per second. G is 9.8 meters per second squared. I'm sorry. A sub y is 2.00 meters per second squared. G is 9.8 meters per second squared plus 1 equals 48.2 newtons. So now let's evaluate if the acceleration is downward. Now it's it's 40 newtons times minus 2 meters per second squared divided by 9.8 meters per second squared plus 1. We get 31.8 newtons. So a little comical part here. Take this advice: if you buy a fish by weight in an elevator, make sure the fish is weighed while the elevator is either at rest or accelerating downward. Funny author. Furthermore, notice that from the information given here, one cannot determine the direction of the velocity of the elevator. All right. Sometimes you can get the same sensations when it's accelerating, when it's slowing down, or when it's speeding up. You can't always tell. Okay. Suppose a woman in the figure retires of watching the scale and exits the elevator. Then the elevator cable breaks, and the elevator and its remaining contents are in free fall. What happens to the reading on the scale? If the elevator falls freely, the fish's acceleration is AY equals minus G. And so if AY is equal to minus G, we see that the scale reading, T, is 0 in this case. The fish appears to be weightless, which is what happens when you, what's the long tower that drops you? I think it's Scream. You feel weightless because you're in free fall for just a moment. Okay, let's now pay attention to the next example. We're going to be doing on Monday. We're going to be doing the Atwood machine. When two objects of equal mass are hung vertically over a frictionless pulley of negligible mass, as in the figure, the arrangement is called an Atwood machine. Atwood machine. The device is sometimes used in the laboratory to determine the value of G by measuring the acceleration of the objects. Determine the magnitude of the acceleration of the two objects and the tension in the lightweight string. Lightweight meaning that we're ignoring its mass. We're going to do this experiment on Monday, so let's dive right into it. Imagine the situation pictured in the figure in action. As one object moves upward, the other object moves downward. Because the objects are connected by an inextensible string, the distance one object travels in a given time interval must be the same as the distance the other one travels. And their velocities and accelerations must be of equal magnitude. So let's categorize this as follows. The objects in the Atwood machine are subjected to the gravitational force as well as the forces exerted by the strings connected to them. Therefore, we can categorize this problem as one involving two particles under a net force. Okay, let's analyze this. The free body diagrams for the two objects are shown. Two forces act on each object: the upward force T exerted by the string and the downward gravitational force. In problems such as this one, in which the pulley is modeled as massless and frictionless, the tension in the string on both sides of the pulley is the same. If the pulley has mass or is subject to friction, the tensions on either side are not the same, and the situation requires techniques we will learn in Chapter 10, so we're still a ways away. We must be careful with the signs in the problem, such as this one. In the figure of the Atwood machine, notice that if the object 1 accelerates upward, object 2 accelerates downward. Therefore, for consistency with signs, if we define the upward direction as positive for object 1, we must define the downward direction as positive for object 2. With this sign convention, both objects accelerate in the same direction as defined by the choice of sign. Furthermore, according to this sign convention, the y component of the net force exerted on object 1 is T minus M1G, and the y component of the net force exerted on object 2 is M2G minus T. From the particle under a net force model, apply Newton's second law to object 1. Okay, Fy is equal to T minus M1G equals M1A acceleration in the Y direction. Apply Newton's second law to object 2. Fy equals M2G minus T equals M2 acceleration in the Y direction. Now, let's add these equations, noticing that T cancels. And so you get minus M1G plus M2G equals M1AY plus M2AY. You solve for the acceleration. Acceleration is equal to M2 minus M1 divided by M1 plus M2 times G. Substitute to find T. T equals to M1G plus A acceleration in the Y direction. And you get, since acceleration with that equals a 2m1 m2 divided by m1 plus m2 times g. The acceleration can be interpreted as the ratio of the magnitude of the unbalanced force on the system, m2 minus m1g, to the total mass of the system, m1 plus m2, as expected from Newton's second law. Notice that the sign of the acceleration depends on the relative masses of the two objects. If m2 is greater than m1, the acceleration is positive, corresponding to the downward motion for m2 and upward for m1. However, if m1 is greater than m2, equation 3 gives a negative acceleration, indicating that m1 moves downward and m2 moves upward. Okay. Describe the motion of the system if the objects have equal masses, that is, if m1 equals m2. If we have the same mass on both sides, the system is balanced and should not accelerate. There's no acceleration. Mathematically, we see for m1 equal to m2, we get ay equals m1 minus, or m1 minus m2, or vice versa, and that equals 0 times g, and so the ay equals 0 equals no acceleration. Okay. What if one of the masses is much larger than the other? M1 much greater than M2. In the case in which one mass is infinitely larger than the other, we can ignore the effect of the smaller masses. Therefore, the larger mass should simply fall as the smaller mass were not there. M1 falls as if M2 were not there. We see that if M1 is much greater than M2, we get ay, it just becomes negative m1 over m1, and then with the m1 overwhelms it if it's much larger than m2, and it just becomes negative g, because minus m1 over m1 is a minus 1, it's a minus 1g. Okay, and we're going to 74. Okay, here's another angle problem, but this time the angle, the mass on the incline has a mass attached to it. A ball of mass m1 and a block of mass m2 are attached by a lightweight cord that passes over a frictionless pulley of negligible mass, as in the top figure. The block lies on a frictionless incline of angle theta. Find the magnitude of the acceleration of the two objects and the tension in the cord. So to conceptualize this, we do the following. Imagine that the objects in the figure, imagine the objects in the figure in motion. If M2 moves down the incline, then M1 moves upward. Because the objects are connected by a cord, which we assume does not stretch, their accelerations have the same magnitude. Notice the normal coordinate axes in the middle figure for the ball, and the tilted axis for the block in the bottom figure. We are free to choose whatever coordinate axes work best for the two objects here. And this is the incline, like we did with the car sliding down an incline. Now let's categorize this as follows. We can identify forces on each of the two objects and are looking for an acceleration. So we categorize the objects as particles under a net force. The object, the block, for the block, this model is only valid for the x prime direction. In the y prime direction, we apply the particle in equilibrium model because the block does not accelerate in that direction. Okay. Let's analyze this. Consider the free body diagrams. We apply Newton's second law in the y direction to the ball, choosing the upward direction as positive. Okay, so the force in the y direction is equal to T minus m1g minus m1a in acceleration in the y direction. And that's equal to mass 1 times the acceleration. For the ball to accelerate upward, it is necessary that the tension be greater than m1g. In this equation, we replace ay with a because the acceleration is only a y component. For the block, we have chosen the x prime axis, where the x prime axis is the tilted one, along the incline as the bottom figure, as in the bottom figure. For consistency with our choice for the ball, we choose the positive x prime direction to be down the incline. Apply the particle under a net force model to the block in the x prime direction and the particle in the equilibrium model in the y prime direction. So those equations are as follows. Fx prime equals m2g sine theta. Remember I warned you about the sine coinciding with the x when you're working with inclines like this. So it's m2g sine theta minus t equals m2 ax and a acceleration in the x prime direction equals m2a, and fy is equal to n, fy prime equals n minus m2g cosine theta equals 0, n being the normal, which is opposite to m2g cosine theta. Let's see if I can remember back where my okay. Notice that we replace a prime x with a because the two objects have acceleration of equal magnitude a. Solve the first equation for t. T equals m1 times g plus a, and we take that top equation. Substitute this equation. Substitute this expression for t, and so m2g sine theta, that's for the x, for some of the forces of x prime, m2g sine theta minus m1g to a equals m2a. And solve for a, we get a equals m2 sine theta minus m1 divided by m1 plus m2, the sum of the masses, times g. Substitute this expression for a to find t, and we get the following. The block accelerates down the incline only if m2 sine theta is greater than m1. If m1 is greater than m2 sine theta, the acceleration is up the incline for the block and downward for the ball. Also notice that the result for the acceleration can be interpreted as the magnitude of the net external force acting on the ball block system divided by the total mass of the system. This result is consistent with Newton's second law. Okay, what happens in this situation if theta equals 90? Well, if theta equals 90, you've got the pulley, you've got the mass on one side and the mass on the incline. If you're up to 90 degrees, what does it become? It just becomes an Atwood machine. If theta equals 90, the inclined plane becomes vertical, and there is no interaction between its surface and the M2. Therefore, this problem becomes an Atwood machine. Letting theta equals 90, we get the following. We get A equals M1 M2 minus M1 over M1 plus M2G, and the tension equals 2M1 M2 divided by M1 plus M2G. I think those are, if we look back, those are the same as the Atwood machine equations. And the last slide on this discussion. Okay, what if M1 equals 0? If M1 equals 0, then M2 is simply sliding down an inclined plane without interacting with M1 through the string. Therefore, this problem becomes a sliding car problem in a previous example. So it describes a mass sliding down a frictionless inclined plane similar to the sliding car problem. That M1 equals 0 in the equation for the acceleration, and you get if M1 is equal to 0, then you get A equals M2 sine theta over M2G, and I think that's the same as what we had earlier. And this ends our discussion of analysis models. We will next discuss forces of friction. All right.